Hello everyone, we'll discuss problem E, MEX of LCMs of round 879. And a small disclaimer, I have not read the tutorial. So this solution passes, my solution passes, but it might not be the most optimal solution. Okay. So the problem statement says that you are given an array, and what you need to do is you need to look at all the sub-arrays in this given array. Suppose this may be a sub-array or this may be a sub-array. So there are total these many sub-arrays in the array. And for all the subarrays, you will find the LCM. You will add those LCMs to a set, and then you have to find the MEX of that set. What is the MEX of a set? It is the first integer which is not present, like the smallest integer which is not present in the set. So for example, if the set looks like 0, 1, 2, 5, then the MEX, suppose these are the LCMs, then the MEX here will be 3 because 3 is the smallest integer which is not present here. If the MEX contained 3, then in that case, if the set contained 3, then in that case the MEX would be 4. If the set contained 4, then the MEX would be 6. Okay, and so on. So the constraints were given that n, that like sum of n array sizes can go up till 3 into 10 to the power 5, and AI was around 1 e to the power 9. So the way I thought about it is I tried to, number one, set some upper bounds on the answer, set some bounds on answer. All right. So since n is equal to 3 into 10 to the power 5, that means the total number of segments, total number of segments, uh, these can be n into n plus 1 by 2. So they will be approximately uh, 5 into 10 to the power 10. They will be less than this, but this is a good upper bound. Okay. They will be less than this number, but this is the maximum like number of segments that may be possible if you apply the formula of n into n plus 1 by 2. Okay, it's actually a little bit greater than that, but that's all right. So what can we conclude by this? We can conclude that the final answer will be less than equal to 5 into 10 to the power 10 plus 1. Okay, the final answer will be less than this. Now, why am I saying this? Because suppose the final answer was greater than this value, greater than 5 into 10 to the power 10 plus 1. So what would that mean? That would mean that the LCMs that in all the possible segments would be like 1, 2, 3, 4. All of these LCMs, because the MEX is greater than this, right? So all the numbers from 1 to 5 into 10 to the power 10 plus 1, they need to be present as LCMs in the original arrays subsegments. But this is not possible because the number of, because see, these are how many? These are 5 into 10 to the power 10 plus 1. But the total number of segments is only this. So like each segment gives only one LCM. So obviously it's not possible uh, to have more number of LCMs than the number of segments. Okay. So we can say, okay, the answer will be less than equal to this. Now, the second thing I thought is, how does the LCM change? Suppose this is your array, right? You have fixed your segment at some I point. Suppose this I is equal to 2. Okay. And one by one, you are increasing the segment's length and you're observing how the LCM is changing. So suppose it's initially 2, then the next element, suppose initially the LCM is 2, right? Suppose the next element is 3. So what will happen is the new LCM will become 6 of like this range. That is, the LCM is multiplied by 3. Then suppose the next element is 6 and you are now taking this segment. So in this case, the LCM doesn't change, it remains 6 only. Suppose then the next number is 8, which is 2 to the power 3. So your LCM of this combined range will increase by 4. You can try it out and it will become, I think, 24. Okay. So we can observe that the LCM number 1, it always increases as you increase the length of the segment. And when the LCM changes, suppose the LCM goes from some X to some Y, it is always like multiplied by some value. Okay. because here it is multiplied by 3, it is multiplied by 4, it is multiplied by some value which is greater than equal to 2. And I hope that is also obvious as to why that happens, because when you add a new number, suppose this was your original segment and the LCM was something like 2 to the power p into 3 to the power q into 5 to the power 7, like 5 to the power something else, and like all the primes basically have some powers. And then if you add a new number here to this segment, then if that number has some, it has maybe 2 to the power p plus 2, and everything else is same, like the new number looks something like this, then the LCM will increase by 2 to the power 2, because now the new LCM will look something like 2 to the power p plus 2 and the rest will remain same. So the point I'm trying to make here is that the LCM will be multiplied by some factor if it increases, but it can also remain the same, like here it was 6. Now suppose the next number here was 2, then the LCM of this combined range was again 24, so it won't really change here. So the LCM, if it increases by some factor, otherwise it remains the same. Now, coming back to this point, can you answer me this question? If there is a segment whose LCM is greater than 5 into 10 to the power 10 plus 1, let's say. If there's a segment whose LCM is greater than this value, and we have fixed the I, do we even need to consider this LCM? Do we even need to add it to our set when we find the MEX at the end? The answer is no, we do not need to, because we have already said that the answer will lie in this range. It will lie in the range of 1 to 5 into 10 to the power 10 plus 1, because these are the number of unique segments you can have. So if the LCM is greater than this, even if it is added to the set, it will be added after this point, and the MEX lies in this range, right? So it doesn't really, adding or not adding it, it will not impact our answer. Also, any point ahead of j, like I to k, and here is j. Since I said that the LCM either increases or it remains the same, this segment's LCM will also be greater than 5 into 10 to the power 10 plus 1. So we can basically stop searching ahead of this for this particular I. Then we will move to the next I plus 1, and then we will search ahead for it again. But for this particular I, we will just search until the LCM reaches this point. Once the LCM of the segment is greater than this value, you can stop. This now, from this point, what we can say is, like I said, if the LCM is greater than this value, then we don't need to search further, correct? And from here, we understood that the LCM, when it increases, it is multiplied by some value greater than equal to 2. So I am asking you another question now. How many times can the LCM change? Can the LCM change till, sorry, bad writing, till it becomes greater than this value? Matlab, suppose initially your LCM is something, suppose initially your LCM is some x, okay? Then the next time it increases after, no, like for this particular I, initially your LCM is x. Then suppose you increase it, and then the LCM increases, like if you expand the segment to some k1 into x, okay? Then the next time it will increase to some k. Originally it was k1 into x, now it will suppose increase by a factor of k2, so it will become k2 into k1 into x, and so on. How many times can this happen? Can you give me a rough idea for this? Well, k is always greater than equal to 2. So after around 38 iterations, it will become, suppose k, let's take the minimum possible value of k, which is 2, right? Suppose k1 is equal to 2 and k2, every time it only increases by 2. So after 38 iterations, it will become 2 to the power 38 into x. And suppose x was as low as possible. X was initially 1. So At the end, it becomes 2 to the power 38. And this number is greater than 5 into 10 to the power 10 plus 1. So from this, we can infer that when we fix some I and we increase the segments, like expand the j, the endpoint of the segment, we will keep expanding until the LCM increases uh, around 38 times. So the LCM, uh, like we are only concerned with the LCM increasing around, you can take it as 40, but let's call it 38 only. So the LCM can at most increase 38 times. All right. Beyond that, beyond that, the LCM will increase, but then it won't be our concern because then the overall LCM will be greater than this value. And like I already discussed before, that if the LCM is greater than this value, then it's discarded. It's not worth our time to explore further. So the problem reduces to this, okay? For each I, you need to find out all the J's, J1, then J2, then J3, such that initially, like at these points, at these J1, J2, J3, the LCM changes. For example, suppose initially the value was 2, okay? The value at index I was 2, and the next value was 6. So, or let's say initially I was 6, okay? Initially I was 6. Then the next value was 2, it was 3, and then it was 8. Okay, this looks better, yes. So at this point, the LCM was 6. Then at this point, the LCM was again 6. Like we are taking this segment. Then at this point, the LCM was 6 again because of this region. But when we reach here, the LCM will increase and it will increase by around 4. The LCM will become 24 at this point. So the LCM at this point changes. So this is 1J. This is J1. So the LCM is now 24. Suppose the next index is 24 again. So the LCM will not change. So we don't really we are not concerned with this. Then suppose the next value is um, let's call it 4. The LCM will not again change. But suppose then the value is 5. So the LCM will now become 24 into 5, I think. So it will become 120. Okay. So this is J2 and so on. So basically, we want to find out currently we're at I. There is some LCM here. Then at I plus 1, maybe the LCM remains the same. At I plus 2, maybe the LCM remains the same. The new numbers which are being added, they do not contribute any new extra power than what was already there. Then suppose at some J, this number actually contributes some extra power. Suppose till here the LCM was something like 2 to the power p into 3 to the power something into something else. And this number was 2 to the power p plus 3. So the LCM beyond this point will increase to 2 to the power p plus 3 into something, right? So at this point the LCM changes. Then we want to find the next point where the LCM changes and so on. And how many points there will be, I already discussed. The LCM can change many times, but we are only concerned with the LCM changing at most 38 times. So at most we are um, for each I we are going to find 38 indexes or less, depending on, maybe there are not even 38 positions where the LCM changes, but at most this much we will find. And then we will store those LCMs in a set and then we will find the MEX. So if you are following me till here, let's discuss how will we do it. And then I will also tell you some additional constraints on the answer that we can obtain further. So how do we do it? Well, suppose this is the index that we are currently on, and we are saying that at some index j, the LCM changes. Okay. So here the LCM was suppose x, and here the LCM was y, and in between at all these places the LCM remains x, like for the subsegment starting here and ending at some position there. So what can we say? And first I will tell you, then we will discuss. So all the what I'm trying to say is that the all these points I plus 1, I plus 2 till j minus 1. If we take the LCM of these points, if we take the LCM of these points, then it will be divisible by x. For example, suppose x was 6, okay? This was 2 and this was 3 and this was 8. So if we take the LCM of this element, suppose, then, or if we take the LCM of these two elements, we know that if we can manually also check, but that will not work in the given time complexity. So I am trying to apply binary search and range LCM queries to identify the next j in log n time. Okay, that's my goal. So if we take the LCM of these two numbers, it is 6, and that is dividing the old LCM, which was initially it was 6 only, right? But so this is a good range, but like um, these two numbers, like the j value will not lie here, it will lie ahead of here, because if their LCM is dividing 6, then they themselves will also divide 6. Okay, and they will basically not contribute anything new to the LCM. But if you take this range for example, then for this range the LCM is 24, which does not divide 6. 6 modulo 24 is not equal to 0. So what we will do is we will start at this index I and we will do a binary search. We will do a binary search, suppose till here. We consider this range first of all. This is our mid value, let's say. And then what we will do is we will compute the, suppose our start was initially this. This was our start. And suppose n minus 1 is the last element. So we want to find the first index where the LCM changes. So suppose this is our end initially. What we will do is we will pick some mid value. Okay, suppose this is our mid. We will check, does that j lie in this region? By j I mean the j1 value, the first time where the LCM changes. If it lies in this region, then what will that mean? It will simply mean that the LCM of this region will not divide the old LCM, because the LCM is changing, right? Somewhere here. That means there exists a number which is contributing something extra than the old LCM. So it will definitely not divide the old LCM, because for dividing, we basically need to make sure, um, suppose this is 2 to the power 3. Suppose the old LCM is 2 ki power 3, 3 ki power q, 5 ki power 7. Oh, wait, not 7. Right? I keep saying 7. Into 7 to the power s, and so on. And then there is a new number. That new number must have some additional power. That number may be of the form 2 to the power p minus 1 into 3 to the power, let's say, q plus 3. Okay. So it is contributing, originally power of 3 was q. Here, this number has power greater than q. So this number will definitely change the old LCM if we consider it. And you can, it's very obvious to see that this value will this value will not be 0. Okay, because um, like this will divide this, right? But then this 3 to the power q will not be divided by this value. So because it's greater than 3 to the power q. So that's why We will just check the LCM in this range and we will compare it with the old LCM to see if it divides it. Suppose like I took this example, right? Our suppose this was our case 6, 2, 3 and 8. Suppose our mid was this, right? This was our mid. So we would check, okay, does this range, the LCM of this range, does it divide the old LCM? It does. So that means that the answer, like the J value lies to the right of this region. It cannot lie in this region. So we will check to the right. So suppose then our um, mid value becomes this. Then we will check, okay, does this region from I plus 1 to mid, does this region's LCM divide 6? So the LCM of this region is 6. So it does divide 6. So that means um, the J value, the point where the LCM changes, will not lie, does not lie in this range. And then finally, suppose our binary search mid is here. Let's say there's a 5 as well here. Okay, let's say there's a 5 here as well. Then suppose our mid, I mean, I'm not following the exact binary search, but suppose our mid becomes this. So then our range is like this. Um, like we are basically searching to the right of the previous range. So we will check, okay, the LCM of this region, does it divide 6? It will not. So this could be our answer. This could be our J, but we will search to the left to make sure that it is our answer or not. So then our mid value will change to something like this. And this region also doesn't, the LCM of this region also doesn't divide. So that means the answer will lie in this range. And that's where we will end our binary search, because we know that the answer doesn't lie in this range, but we know the answer lies in this range. So obviously this has to be the answer. Okay, so you can simply just binary search on the J value. And once you have found this J, what you will do is you will increase your LCM, like you will move from this to this, and then you will try to find the next J, and so on. Now, one question that we will not may come to your mind is, how do we even calculate the range LCM? Because the numbers can be very large, and do we store the product or what? So the first thing that may come in your mind is something like a range data structure, which is maybe you can use a segment tree. But the drawback of segment tree here is we already have a lot of computations happening. How many computations? For each index I, we have um, around 38 J's that may exist, like we discussed. And to find each J, we are doing a binary search of order log n time. So the complexity, the total computations will be something like n into 38 into log n. And if you compute it, then this is what it comes out to be. Um, because n is like 3 10 per 5, and this is also this is around 18, and then this is how much it is. So it is 2 into 10 to the power 8. 1 2 3 4 5 6 7 8. Okay, so this is around 2 into 10 to the power 8 computations, and around 5 into 10 to the power 8 computations is a uh, safe bet for 1 second. Okay, so this is very close to 1 second, and if we use a segment tree to find the range LCM, then we would have additional log n time. Like you just basically multiply this by 18. So which would then exceed the time limits of 2 seconds. So we want a better data structure, and for that we can use a sparse table. So if you don't know what a sparse table is, basically it is like a DP table, and DP of ij uh, stores some value for the range I to I plus 2 to the power j minus 1. So basically at point I, if you look at some region of length 2 to the power j, in our case we will store the LCM of this range. Okay. Also, there are some um, additional factors here. For example, you are going to be computing the GCD, so it's gonna be um, like when you find LCM, you also need to compute the GCD, right? So for GCD, there will also be some constant factors. So that's why we don't really want this segment tree to be here. And using a sparse table, suppose you want to find the LCM of L to R, right? So you will try to find a power of 2, a power of 2 which exceeds L plus R by 2. And then um, you can sort of do a query. Suppose there is a power of 2 equals to k. Suppose this is uh, length 2 to the power k, and this is also length 2 to the power k. So you will be able to find the answer for this range in order 1 and for this range in order 1, and then you can combine them. So effectively in order 1 time you can find the LCM of an L2R range. If you don't know sparse tables, then I would suggest you to read it. I will not explain it here in this tutorial, but I will link some very good resources for you to learn it. Now, some other minor things that you should take care of. Okay, so this seems to pass, although it's very close to the like to the actual time limit. So it took 1200 milliseconds. Uh, it's not very close, but I have made a lot of optimizations here. For example, I have removed the int long statement, which I usually use. Um, and now I will tell you a few more things which can help you like make the code a little bit more optimized. So this is like all you have to do for each index I. You want to find all the j's where the LCM changes, and you will then add those LCMs to a set, and then you can then find the MEX of that set. Okay. Now, few more things that I want to discuss with you, which are important. So suppose what I told you that for each index I we have 38 LCMs that we are looking at. So in total, there will be n into 38. So 38 into n LCMs will be there, which is around 1.14 into 10 to the power 7. If you put in the value of n, which is 3 into 10 to the power 5. I think this is how much it is, right? So that means that there are only these many unique LCMs that we are concerned about. Initially, at the very beginning, I gave you a rough bound on the answer, which was around 5 into 10 to the power 10 plus 1, because that was the number of segments. But then we talked about how we only need 38 LCMs uh, per I, per left point of the segment. So that way we can say that we need only 38 into n LCMs, and that means that we have only these many unique LCMs that we are concerned about. And by that, what we can actually say is that um, the answer will be less than or equal to this value. The answer will be less than this. All right. So previously we had a constraint on answer here that we talked about, that the answer will be less than this value. Let me zoom in a little bit. Uh, but now we have a better constraint, as even a smaller constraint on the answer, that it will be less than this value. And with this new information, you don't really need to use longs. Okay. What you can simply do is, suppose you are how do you calculate the LCMs of two numbers x and y? You will do x into y upon GCD of xy. And if you want to find the LCM of a range from L to R, you need to do it iteratively. So first you will combine these two numbers, you will find that LCM. Then you will take that as x and the next number as y, then you will combine them and find the new LCM. Then that new LCM will be x and it will be combined. Um, with the next, in case you're wondering on how do you find it for a range. And in sparse tables, we are using that same concept. So this is what the LCM looks like. So even if any of these term, if this term is greater than a rough bound, let's take 1 e to power 8, because our answer is basically any LCM which is greater than this value is also useless for us now. Previously, we had this bound, like any LCM greater than this was useless, but now we have come to a better bound. So any LCM which is greater than this value is useless for us. So suppose we are uh, combining two numbers, right? When we are finding the LCM, and any of these number is greater than 1 e to power 8, let's say, then it's obvious that their combined LCM will also be greater than 1 e to power 8. So in that case, you can just stop. You don't really need to go any further. Okay. So because otherwise the value of LCMs can be very large and you have to take care of overflows. So you can just check if X and Y, any of these values are greater than 1 e to power 8, then you can just stop. Okay. Like the tricky part here is now the range LCM queries. For that, you can initially start with the segmentary solution. Make sure it is working fine. It will give you a TLE, and then you can read about sparse tables, and it's very simple um, and how you can find the LCM using sparse tables in order one. So I will show you my code now. Um, so this is some template for the sparse table, and this is how do you find the range query value. Now look here, right? Like I said, when you want to find the range from L to R, we find a power of 2, which so that we cover at least. So when we are making a query for L to R, we find a power of 2, which such that from L to that, if we add if we do L plus 2 to the power k minus 1, then that should be, I think, greater than L plus R by 2, if I am correct. Yeah, I'm quite sure. I'm quite sure that's the thing. So we are just finding that power here, and then we look at the LCM in this range. We look at the LCM in this range. Since there are some common elements, but that will not impact the overall LCM. Now I just want to combine these two numbers, like V1 and V2. I want to find their LCM, which will be V1 into V2 upon their GCD. So I have added a check here to just make sure that um, like I told you, the upper bound of 1 e to power 8, but we can even reduce it further. I will show you the other summation that has, I think, 1 e to power 8 being used. Yeah. So I just made sure that V1 and V2 both were, if any of them was greater than 1 e to power 8, then we returned infinity, just as a way of saying that the LCM is too large and we don't really need to include it. And then overall, after combining the two numbers, if the LCM is again greater than 1 e to power 8, we return infinity. So this is how you, this is basically the code for finding range queries. Then this is the sparse table construction here. Okay, everywhere you will see this, right? When I'm combining two numbers, I'm making sure that just a way of preventing overflows, because when you multiply the two numbers, like the product can be quite large. So if both are less than 1 e to power 8, then the product will be 1 e to power 16, and that can fit in a long range. Then we go over each index, like each I, to make it the left portion, and IDX will represent where the LCM changes. So um, we are doing a binary search. We are doing a range query from IDX plus 1 to mid. If it is equal to int max, that means it's very large. Then we search to the left. And if the LCM is not dividing the current LCM, like the new LCM is not dividing the current LCM, then uh, that could be our possible J, and we search to the left, otherwise we search to the right. And then we compute the new LCM, as NP is basically the J where the LCM changes. So only that element will be used and the old LCM will be used to compute the new LCM. And then we update it, we update our index, and then we want to search to its right. This is another check, because if I'm not sure if this is needed, but I just checked if the j value, the array at the, the array value at index j, or NP I've called here, if it's greater than 1e to the power 8, then that means the LCM would also be greater than 1e to the power 8, and then we can just stop. We don't need to search further. And then finally we find the MEX. If we for MEX we don't need to do any optimization. We can just difference LCM is the all the different LCMs that we have found. It's a set, and we just search in that set. So that is how you. This is one way of solving it. I have seen other people's solutions which have around 300 millisecond time. So um, I haven't read it, but I would suggest you to read the editorial. Maybe it has some other method. But this is how I thought about it. I hope it helped you in some way. Thank you for watching the video. Bye bye.